so this is practice exam 11A, and we are going over the orthogonality concept. So for those of you who've not ever heard of the word orthogonal before, in geometry, and here, it pretty just means that they're 90 degrees away from each other. So they're perpendicular, they're 90 degrees out of phase, however you want to call it. That's what we're looking for. And by definition, if two functions are orthogonal, when you evaluate their integral of the product of the two functions, it will equal 0. So that's how you know whether the set of functions is orthogonal. So all we're going to do here for 11.1 is we're going to test that these two functions are orthogonal or not. So our first step, we're just going to multiply them. So we have something nice and pretty to plug into our integral. Okay, so when you multiply this out, you should get 3x cubed plus 9x squared, and that's a -9. I don't know what's up with me putting positives everywhere today. Minus 9x squared plus 8x minus 2. Okay, so parentheses, dx, and then our bounds for our integral are just going to be the interval of interest. So going from 0 to 2. So when we take this integral, you should get 3 over 4 x to the 4th minus 3 x cubed plus 4 x squared minus 2x. Okay, and then being evaluated at our bounds, so 0 and 2. Okay, so obviously this lower bound is going to force this whole function to 0, so I'm just going to evaluate it at the upper bound. So we have 3/4 times 2 to the 4th minus 3, 2 cubed plus 4, 2 squared, and then minus 2 times 2. So when you evaluate these, you should get 12 minus 24 plus 16 minus 4, which, lucky for us, goes to 0. So we can say that this set of functions are orthogonal to each other. Okay, so that's the first part. Hopefully it's not too bad. I know since we've been doing a little bit more complex math, it may be weird to just be taking integrals. But so if you need to brush up on that, like I know I definitely do, just taking basic integrals because I don't need to a whole lot. Okay, finally, I got it. Okay, so I'm going to make this smaller so we can work on the rest of our problems. Actually, I'm going to make it tiny. I'm going to make it really small. Okay, so for 11.2, we're asked to find the norm of a different function here. So again, that's something that we have by definition. So by definition, we know that the norm of x equals the square root of our integral from a to b of this function squared. Okay, and please don't forget to square it, and please don't get confused with this square root and the fact that it's being squared and think you can just ignore it, because you have to evaluate the integral before you can rectify anything with the square root. So please keep that in mind. So we have our norm of x, okay, equals, and then for our bounds, we're just going to use the bounds that were given to us. So we have an integral from 0 to 1 of our phi, and our phi is just this equation here. So we have 5x squared plus 3, and the whole thing is squared. Okay, 5x. So squaring this out, you'll get the square root of the integral 0 to 1, 25 x to the 4th plus 30 x squared plus 9, and still a dx. Please be careful about your interval notation, because the style that Dr. Noring's giving these tests, he did say he's going to be a little more rigorous on like actual math grammar. So please don't forget to close your integrals. Just keep that in mind. Okay, so now evaluating this integral, we now have our phi of x equals the square root of 5x to the 5th plus 10x cubed plus 9x. We're still evaluating this at 0, 1. Obviously, our lower bound pulls the whole function of 0, so I'm only going to use the upper bound. So we get that our norm of x equal to the square root 5 times 1 to the 5th plus 10 times 1, 10 times 1 cubed, and then plus 9 times 1. So you should get the square root of 5 plus 10 plus 9 equals the square root of 24. Okay, and then if you want to write it in its most reduced form, you can do this. I know a lot of people, the last time we needed this process, a lot of people got a little bit confused. So that's how you do it. I don't really know what it's called. I learned it in like the 10th grade, and my teacher called it like the tree method. So if you guys have any other ways that you know how to do this, feel free to share it with me or in the group chat, because I know not everyone was taught this in high school, and it might be harder for some people. So since there are 2 2's, we can take it out. It gives us 2 root 6. And if you want to plug it in, you'll see that these two are exactly equivalent, but this is the more technically correct term for that. Okay, and then for 11.3, we're just going to normalize the function, which sounds a little scary, but I promise it's not. So I'm going to make all this real small so we have room to normalize our function. Okay, so when it says to normalize the function, okay, so I guess the important thing to know here is that when an orthogonal set is multiplied or divided by a non-zero constant, it remains orthogonal. So that's the important concept that you're supposed to get from this problem, is that that it's still going to be orthogonal, and when you multiply or divide by the norm, which we found in 11.2, that's normalizing the function. So all we're going to do is we're going to take this function right here. So we now have phi in the norm. Well, I was going to say norm, but you know what I mean. Norm, and we're going to take this whole function, 5x squared plus 3, And we're just going to divide by the norm that we found. So you can divide by the square root of 24 or 2 root 6. So I'm just going to do square root of 24 because it looks easier. Okay, and then if you want, you can break this up. I know Dr. Norn did on his answer key, so it might be something to keep in mind, but it's not more technically correct than the other, being that neither of these are reducible. Yeah, okay, so that is 11A. Please let me know if you have any questions